And at this point, we'll bring up someone who should need no introduction. Arvind, come tell us about emission events and the application of Feast and other tools.
I wanted to thank all of you for being here. I know I'm supposed to be talking for the next 20 minutes, but I'm going to keep it short to make sure that everyone has enough time to enjoy the rest of the evening. All right, so what I'm going to be doing today, or in this talk, is not to give you a lot of additional new information that we have worked on over the past year, but to really bring a lot of the stuff that we have worked on together into one coherent story. And to do that, I've chosen the topic of emission event statistics and its implications for the Methane Fees and the Inflation Reduction Act. So many of the slides I'm going to be showing now are something you might have seen over the course of the 2 days. There have been students and researchers who presented. Professor Dorrit Hammerling this morning presented information on continuous monitoring systems. But what I'm going to talk to you today is how we think about emission events, which is the intermittency and duration of intermittent emission events across different projects and across different types of measurements, and how do we extract information about them, and how do they all come together to sort of help us understand emission event statistics and the importance of the frequency and the duration of intermittent emission events. All right, so what you're seeing on this slide on the left is sort of a cartoon image of how we think about intermittent emission events. So on the x-axis, you have event duration. On the y-axis, you have event emission volumes. And as many of you know in this audience, there are a whole range of duration and volume combinations. Routine tank flashing, for example, might occur for just a few minutes. And the amount emitted depends on the amount of dissolved methane in the liquids. Malfunctioning pneumatics, intermittent bleed pneumatics that stops being intermittent, then has a long emission, that's an upset condition. So it might have a long event duration, but might have lower emission volumes. Upset conditions, things like stuck dump valves that can result in a high volume of methane emission, is something that could be detected in the course of a few hours to a few days. So what you're seeing here is a number of different emission events at oil and gas facilities with a range of emission volumes and emissions duration. And so if you think about how do we estimate emissions from all of those intermittent events accurately, you can end up with a picture that's on the right. So total emissions is, it's a combination of routine emissions that we already know and emissions from these large intermittent events. How much does your large intermittent events shown in purple add to your routine emissions really depends on how well you know about your own intermittent emissions. And in this case, the relevant parameters are the frequency of these events. How many times does this event occur on your facility? It could be once or twice a year if it's a maintenance activity. If it's something that's more routine, it could be once or twice a few weeks, or it could be every single day. You need to know what the frequency of those emissions are, and you need to know what the duration are. Are they fixed within a few hours, or do they happen to emit until the next leak detection survey you do, which could be as long as 90 days or 180 days. And so depending on what your assumptions are and what the right number is for your intermittent emission events, you can have a very large contribution from intermittent emission events, or you'll have a reasonably small contribution from intermittent emission events. The point is to know your total emissions estimates accurately, you need to know what the frequency of these events are and what are their duration. I'm going to give you some examples of what we have seen in many of the projects that MDill researchers have been working on. All right, so this is the QMRV work that we did last year. The paper's already out, and what you're seeing here are methane emissions from tanks as measured by Bridger Photonics and CCOPS. Those are the two different colors, across about 13 sites in 2 different basins. Each dot is an individual measurement taken over the course of a few weeks. What you can see here is that the range of emissions. There are times during these measurements when you don't have any emissions from these tanks, which means the tanks are not emitting. But there are also times when the tanks are emitting more than 1,000 standard cubic feet per hour. And so what this work demonstrated was that across all the basins we measured, there are significant temporal variations in tank emissions. And so the question is, what is the duration of these emissions when they occur, and how often do they occur? And so those are important questions we need to know to be able to estimate what the total emissions or emissions intensity from this facility or from this region. That's example number one. I'll give you a second example. Now we are moving to the midstream. This is a project that we did in the state of New York, measuring methane emissions from compressor stations using Champion X mass balance measurements. So I'm going to walk you through what you're seeing here. The blue dots are the compressors at the compressor station operating. There are, every compressor station might have 1 to 9 different compressors. Not all of them have to be operating all the time. And so the blue dots tell you when we did the measurement, how many compressors, the equivalent of how many horsepower was operating at the time of measurement. The yellow dots, as you might have guessed, are emissions. And so what you're seeing here are 2 transmission compressor stations on top and 2 storage compressor stations on the bottom. Over different days of measurement, so we did about 10 days of measurements. We went back every single day to these sites to measure emissions. What you're seeing here is large variability in compressor station emissions. You also saw a talk from Dan Zimmerle yesterday showing how notoriously difficult it is to measure total emissions from compressor stations. Example number 3. You saw this yesterday. Dr. Lira Wang presented how we can construct measurement-informed emissions inventories by combining statistics of observations from measurements as well as operational information. So the Bridger measurement was very large, about 31 metric tons over the course of 3 months. And then we developed a measurement-informed inventory model that accounts for the fact that tanks were only emitting 4 to 5% of the time. And so yes, if you see it, it's large, but only 5 out of 100 tanks are emitting at any given time. So you account for that emission event frequency, you come up with something like measurement-informed inventory model. And then when you, of course, talk to the operator, they'll tell you additional information that influences some of the assumptions in your model, and you get an even more improved estimate of emissions. And so intermittency, both the frequency and the duration of these events, play a critical role in developing measurement-informed emissions estimates. And I myself showed this graph on one of my talks when talking about feast and equivalence. And what we're saying is that contribution from intermittent emission events strongly influence the effectiveness of methane reduction policies. How? Think of an aerial survey technology that you're deploying in your facilities. If your intermittent emission events, and say you're doing monthly surveys at these facilities using Bridger or some other aerial system, if your intermittent emission events are of duration, say, more than 30 days, say 45 days, which means if you're doing a monthly survey, you're going to catch that intermittent emission events. But if your intermittent emission events are of the duration of 1 day or even a few hours, the probability that you'll actually see that intermittent emission event while you're flying over is very low. Because the frequency at which you fly once a month is much longer than the duration of the event, which can be less than 1 day. So the question is, when we think about intermittent emission events, and you're thinking as an operator or as a scientist thinking about deployment, which of these technologies would be most effective in detecting and therefore mitigating intermittent emissions? Is it quarterly OGI, monthly satellite surveys, monthly aerial surveys, or continuous monitoring systems? The answer is going to depend on what type of intermittent events are you having on your facilities. Are these very short duration, high volume events? Or are these lower volume but long duration events? And that somewhat determines which technology you're going to be choosing here. And so why did I give all of this preamble to intermittent emission events and the frequency and the duration of all these events? Is some of the recent US policies and proposed regulations, such as the updated GHGRP and the methane fees, require accurate estimates of intermittent large emitter events. So this is just sort of a very broad overview of what these changes are, right? In the updated subpart W, you have large release events. That says, if you have an instantaneous emission rate that's over 100 kilograms per hour, or if you have a total emission that's 250 metric ton CO2e, you have to estimate those emissions separately under the category of large release events. And the duration of those events, there are a number of criteria in the updated rules, but you can get it from operational data if you know when the start time and the stop time of that emission is. But if you don't have any data, then the duration default is however long it was until your previous survey. So if you're an operator, if you're doing quarterly surveys, that means the duration for that event is 90 days, unless you have some other operational information to tell you the duration was much shorter than that. Dan Zimmerly, I don't know if he's in the audience, but he made this really cool graph and he put it up on LinkedIn, so I stole it from there and put it up on my slides. And this is what I'm showing right now. This is a much more elegant way of showing what I just told you, right? So you have the emitter size on the x-axis from 1 kilograms per hour all the way to 1,000 kilograms an hour. And on the y-axis, you have the amount of time, the duration of your emission it's going to take to exceed that 250 metric ton CO2e per event threshold to be reported under the updated GHGRP proposal as a large event. So if it's anything greater than 100 kilograms per hour, sort of the blue shaded region, you have to report it as a large emitter event. But if it's less than 100 kilograms per hour, then you have to check whether, based on the duration of that event, does the total exceed 250 metric ton CO2e. That's sort of the brown or the yellowish color there. So if you have an event that's, say, 30 days long, a month, all you need is an emission of 13.9 kilograms per hour. So if you have a 14 kilogram per hour emission rate that lasts for 30 days, that will exceed the 250 metric ton CO2e per event threshold, and you will have to report that under large emitter events. So all of this to say that it's really important to think about how we improve our own estimates of the frequency and the duration of these intermittent emission events. And so I'm going to talk about now how we are developing different approaches to estimate emission event frequencies. So what's the best approach to do this? And you have seen many talks over the past 2 days that sort of highlight this area. For example, you just heard this morning about using continuous monitoring systems to develop algorithms to identify emission events and their frequency and duration. You know, the Minds team is working on it, Dave Allen's group is working on it, a number of people are working on developing all these algorithms. We can use large area surveys, aerial surveys, truck surveys, satellite measurements to develop basin-wide estimates of emission event frequencies. The UT and CSU have been working on this for the past year or so. And then you can use a combination of measurements and operational data to build distributions of emission event frequencies and duration. This is going to take time because we talk to the operators, we go over every single emission we saw and say, okay, what do you think is the duration of this? Do you have any evidence showing that the duration of this event was 96 hours or 120 hours? We do this over time slowly, so we can build a distribution of the duration of emissions for that operator. And we can do it for different basins as well. So I'm going to give you sort of, for these three approaches, I'm going to show you some examples of how it's done. I believe you saw this animation earlier this morning. This is an animation of a methane emission source that's shown in red. And there are multiple sensors around the site. So we are looking at sensor 1, 2, and 3. And as the wind blows in different directions, the signal goes over different sensors. So what you're seeing on the left are sort of what the signals on sensors 1, 2, and 3 look like. Now, this is an interesting example. So you combine your emission with some kind of dispersion modeling, and you can estimate what your sensor signals are. The really challenging problem is, of course, going backwards. All you have is this information. You need to get that from this one. And that inverse problem is a much harder problem. But the Minds team has developed a lot of interesting algorithms to think about, in a statistically robust way, how do we go from this to an emission rate number. And so we tried that with one of our first QMRV projects. Can we do this for simple production sites that do not have a lot of complexity? And what we were able to do is this. This is the distribution of the frequency of events and the duration of emission events. So for a particular basin, we observed data over a 6-month period from continuous monitoring systems, and the algorithms that Minds developed has been used to develop these distributions. So on the left, you have the duration distribution. On the right, you have frequency, also time between emission events. So you can see that many of the events actually happen on a daily basis. For example, if your continuous sensor is detecting tank flash emissions, it's going to happen on a regular basis. But there are also events that happen at much lower frequencies. For example, we have a data point here that shows there's an event that happens once every 25 days. Now, we haven't gotten into the root cause of why this happens or what that event corresponds to, but this is the kind of analysis you could do potentially with continuous monitoring sensor data, and this kind of information is going to be important to think about what your total emissions are, and therefore what your methane intensities are, because that's what the methane fees in the Inflation Reduction Act will be based on. Again, how do you do this with aerial surveys? So this is a slightly different project where we looked at sort of data from a lot of different basins from a number of different aerial surveys. And you can look at, okay, when you do these surveys, at what frequency are you seeing emission events? And so this is data from one of those analyses. So you have 4 different basins, the Bakken, the Anadarko, the Eagle Ford, and the Permian Basin, and you look at event frequencies. You can do this for individual equipment, but here we are just looking at how many events are being observed. So it was 1.1% in the Bakken, but it was 8.9% in the Permian Basin. And this kind of information is really helpful when individual emissions inventories at facilities and regions and operators are becoming more important in the context of all the new policies we just talked about. And so we do observe significant differences in emission event frequencies across basins. And I'm sure folks that have done a lot of measurements in the room would have observed similar differences even across operators in the same basin. And the third example is, as I said, combining measurement data with operational information, and you heard about that from Dr. Lira Wang yesterday. So what you have are frequency of emission events. We get this from measurements, from doing aerial surveys. Then you have the distribution of the duration of events. You can get that. One example was the continuous monitoring systems. But in this case, we can build it from operational information. It's SCADA data. It's looking at the logs of what went wrong, doing root cause analysis of the emission sources that we observe from measurements. The point is you can build distributions of duration. So you combine the frequency with the duration and the emission rates, and you can build measurement-informed emissions inventories at the site level. Now, there's a lot of uncertainty about these things. You've heard a lot of talks about, several talks today and yesterday about how do we quantify uncertainty, and all of that work remains to be done. But this is one way of thinking about how do we estimate the frequency and duration of intermittent emission events. So now I'm going to go back to one of the first slides I showed you, the combination of emissions from routine events and emissions from large intermittent emission events. So this is the graph you saw before. How much the large intermittent events contribute to your total emissions depends on the frequency and duration. Now, translate that into emissions intensity. So this is a simulation of event duration on the x-axis. So it can be anywhere between a few hours emission event all the way to an event that lasts for 30 days or a month. And on the y-axis, you have event frequency. This is the number of events per day. You can start with, on average, 0.1 event per day, all the way to about 5 events per day, which is a lot of events. And what the color map is showing you is emissions intensity. So for this site, if you did not have any intermittent emission events, the nominal intensity of the site is about 0.5% methane leakage, which is fairly low considering what we measure. But depending on your assumptions around your event frequency and your event duration, you can go as high as 10% methane emissions intensity. As many of you know, the methane fees are based on intensity numbers, about 0.2%. So if you don't estimate or if you don't calculate your event duration and event frequency accurately, you will get a range from 0.5% all the way to 10%. And I don't have to tell you the implications of having a 10% leakage rate on paper and the methane fees associated with it. So this kind of analysis where you think about different ways of getting accurate information on your emissions frequency and your duration is going to be very important to how you estimate your total emissions intensity, which again will then affect how your methane fees are calculated. But with that, I'm going to summarize. So how are we going to collectively develop accepted approaches to improve understanding of emission event statistics? So the updated GHGRP and the methane fees in the Inflation Reduction Act require accurate estimates of the frequency and duration. And this is a complex challenge. I mean, all of the examples I showed you are not definitive answers. Those are just starting points in a race where we have to figure out how to do this accurately. So these are all some of the approaches that we here at MDL have been trying. It requires integration, it requires synthesis and interpretation of information from multiple independent data sets and campaigns. So all of the slides with data I showed you today were from 5 different projects that were run independently by several people in this room. But the point of starting MDL for us is to precisely do something like this. Bring all of this together, bring all of the independent studies, disparate measurements that are being done, and bring them together to understand what all of that means going forward for US oil and gas methane policies.